Hello, good morning, if it's morning for you, and welcome to another edition of Math, Music, and More. Today's video is actually going to be pretty quick because there was something that was kind of gnawing at me about yesterday's video regarding power sets, their size, a proof by induction that it could be extended to infinity, and the actual application to the infinity, and the notion of a binary code where every single placeholder represents a natural number, and therefore the binary code is just a choice function of all the different natural numbers that are included in the power set. That was all great, and I was very moved by it, as I pointed out, the beauty, the interconnectedness of things. But there was nevertheless something that was gnawing at me, and it was the proof by induction that I showed to all of you. So I just noodled around a little bit again this morning, that it suddenly came to me, yep, it was wrong there, but the result is still correct. I'm going to show you a slightly different proof, and that's my sole intent for today's video. So let's go back to the board. If you remember, we already showed that it holds for n equals 1. 2 to the 1 obviously equals 2, and we assume that it holds for 2 to the n, and then we have to use that to demonstrate that it also holds for 2 to the n plus 1, the typical protocol for proof by induction. Well, what we said last time was that we break up 2 to the n into components, the null set, and then 2 to the n minus 1. This and this is the same. We just removed one of the elements. And then I had said that if we go to the n plus 1 version, we still have the null set, and we still have all these same elements, but then we will infuse into each of these also another version with the nth plus 1 element, and therefore we would have 2 of these. But then, of course, we also have the larger set, which I call tau. That was the mistake. If you think of this chain of elements, 2 to the n minus 1, the very last one is the total set. If it already is the total set, then multiplying it by 2 means we already have created the new, larger total set by adding the nth plus 1 element. So we have to remove that tau. That can't be there. That tau is already embedded in here. But this doesn't give us the result we want. Is there something else we could do? Yes, there is. And what is it? Remember that the power set needs to include the null set, the entire set itself, and every possible subset, including the individual elements. Well, if we're going to n plus 1, that means we have to add the nth plus 1 term, which I'm denoting here as a sub n plus 1. That's the trick. That's the proper proof. Because how does it flow now? Well, we have the null set, that's 1. And then we have 2 to the n plus 1. I'm just multiplying this first term by 2. Oops, that's a minus 1 down here, not in the exponent. And it's minus 2 and a sub n plus 1. Well, this is 1 plus 1 is 2. This is minus 2. Cancels. We're left with 2 to the n plus 1. So there you have it. There's the proper proof. My apologies for the mistake. But I love doing stuff like this because it shows you once again that when you're thinking and you're building and creating, don't just do analytics. Sometimes trust your gut. If something is bothering you, there's a reason for that. Go back, peel back the onion, dive in. So anyway, I hope you enjoyed this video. And the other bizarre little cliffhanger, although perhaps cliffhanger is the wrong term to denote what I'm about to explain. Did you find it interesting that I used the letter tau to describe the entirety of this set? There was, I think, a subconscious reason why I did that. Because for all of you that have ever studied topology, isn't it interesting that the definition of a topology and a topological space in this way very much resembles our very definition of the discrete world of power sets, where you have individual objects of elements and then all the discrete combinations of those elements to totality, as well as from the null set and every combination in between. It very much resembles the continuous homeomorphic world of topology. Unfortunately, I forgot all that stuff. Again, it's been decades since I've used any of this in my life. So if you make any requests for a topology and can you prove this and can you prove that, oh my God, I'm gonna have to dive back in and reteach myself everything. Anyway, go out and have a great day. Thanks for allowing me to make the correction. Hope you enjoyed it. Take care, everybody.